To run the most demanding modern applications, a top-tier graphics card must execute approximately 35.6 trillion calculations per second. Processing data at this scale forces a choice between two different ways of handling data: optimizing for the speed of a single task or the total volume processed across thousands of them. A central processing unit, or CPU, is built for the former. It uses a small number of complex cores to rapidly switch between different tasks, minimizing the time it takes to complete a single instruction. A graphics processing unit is specialized for embarrassingly parallel computation, workloads where millions of identical operations occur simultaneously without needing to coordinate with each other. To maximize this throughput, a GPU dedicates nearly all of its physical silicon exclusively to simple arithmetic calculators. Understanding how modern parallel computing works requires looking at how engineers physically mirrored the mathematics of linear algebra in the hardware. When those outlier calculations are required, the data is routed to a much smaller set of special function units located elsewhere on the chip. By stripping away generalized logic circuits, hardware engineers maximize the raw arithmetic density of the silicon. To scale this computational density, 32 individual cores are bundled together into a structure called a warp. 4 of those warps are then clustered to form a streaming multiprocessor, or SM, the primary processing block of the architecture. This block runs on an execution model known as single instruction, multiple threads, or SIMT. Older architectures relied on a lockstep model called SIMD, where every thread in a warp had to execute the exact same instruction at the exact same time. If one thread stalled, the whole group stalled. SIMT breaks that gridlock. It provides each individual thread with its own distinct program counter, allowing them to process at varying independent speeds. Giving each thread autonomy solves warp divergence. If a block of code contains a data-dependent conditional branch, the hardware can evaluate different paths efficiently without forcing the entire processor to wait. Engineers physically embedded a shared 128 kilobyte L1 cache inside each SM, allowing separate threads to instantly grab and reuse localized data output by their neighbors. The SIMT hardware scheduler operates as the critical mechanism that coordinates thousands of chaotic, independent threads into a synchronized parallel output. This architecture is specifically tuned for practical workloads like 3D vertex transformation. This animation shows a 3D wireframe object being mathematically converted from isolated local coordinates, model space, into a shared global grid, or world space. This mathematical transformation requires taking the exact same coordinate addition instruction and applying it to millions of individual vertices simultaneously. Because every single one of those addition calculations has absolutely zero dependency on any other point, they are perfectly suited for parallel execution. The GPU's gigathread engine captures this immense zero-dependency workload and instantly distributes it across the thousands of available CUDA cores. The physical die is molded specifically to ingest and process these zero-dependency matrices at a scale a traditional CPU cannot match. Processing 35 trillion operations every second creates a severe physical consequence: extreme data starvation. A standard CPU relies on a 64-bit memory bus, moving about 64 gigabytes per second. A high-end GPU utilizes a massive 384-bit bus architecture, capable of transferring 1.15 terabytes per second. Physical constraints on the circuit board limit how many traces can be added, necessitating a shift in the electrical signals used to move bits. Engineers moved beyond binary transmission, the standard sequence of ones and zeros, to multi-voltage encoding schemas. This graph compares a simple two-state binary square wave against the PAM3 encoding standard, which utilizes ternary states, a positive voltage, zero voltage, and a negative voltage. Using this specific math, the PAM3 scheme compresses 3 standard binary bits into just 2 ternary digits. Transmitting fewer physical pulses across the wire increases the total data transfer rate while improving the signal-to-noise ratio over traditional binary lines. Infinite mathematical throughput on the processor die is entirely useless without redesigning the physics of how data travels across the memory bus. Modern computing demands, especially those driving neural networks, now require mathematical operations that exceed simple fused multiply-add logic. To process these workloads, hardware engineers designed the tensor core, a logic block built explicitly for massive matrix multiplication. This animation shows how tensor cores behave differently. They ingest 3 entire matrices simultaneously. Rather than executing sequentially, the core completes the multiplication and addition for all overlapping variables concurrently in a single clock cycle. True hardware acceleration requires evaluating entire structural matrices instantly, cementing the GPU as the physical foundation for generative computation. These complex structures are carved into silicon dies containing up to 28.3 billion individual transistors. Manufacturing at this microscopic density guarantees that patterning errors and dust particles will physically damage certain sections of the silicon. However, the massive repetition of the streaming multiprocessor architecture provides an inherent manufacturing resilience. Engineers perform a process called defect binning. By permanently isolating and deactivating a physically damaged streaming multiprocessor, they avoid trashing the entire 28 billion transistor die. Chips with deactivated cores are categorized and sold as lower-tier models, while the flawless dies become the flagship graphics cards. From the stripped-down FMA logic gate through the SIMT thread schedulers, across the ternary memory bus, and down to the defect-binned die, the modern GPU is the physical embodiment of parallel algorithms carved directly into hardware.